Alright, this is going to be a short video on a couple examples of integration by tables. So we're going to actually derive one of the formulas. This is listed as formula 35, which says that the integral of du over u squared, square root of u squared plus or minus a squared is equal to minus plus square root of u squared plus or minus a squared divided by a squared u plus constant of integration. And one thing we might make a comment on is about the plus minus. So for example, if it's plus here, it's going to be plus here, but it'll be the opposite sign. It'll be a minus sign right there. Similarly, if it's minus here, it's also going to be minus here, but it'll be the opposite sign. It'll be plus here. So we're going to actually use some trig substitution to go ahead and integrate this thing. Okay, so the first thing we're going to do is we're going to look at the positive case here. So we're going to look at this here. So we're going to look at the integral of du over u squared, square root of u squared plus a squared. And so that looks like we can probably do a setup with a tangent here. So tangent would be opposite over adjacent, so opposite side would be u, adjacent side would be a, and then we use the Pythagorean theorem, and the hypotenuse will be u squared plus a squared under the square root. So the tangent of theta will be u over a. So then if we solve for u, because we want, basically when we're doing the trig substitution, we want to replace all the variable of x, or in this case u, with variables in terms of trig functions of theta. So we'll go ahead and multiply by a, so we got a tan of theta is equal to u. Okay, and so that'll give us a relationship for the u, and then we also need a replacement for du, so a secant squared, so we'll go ahead and do the differential of both sides. So a secant squared of theta d theta is equal to du. Likewise, if we take this equation here and square, we would have a squared tangent squared of theta is equal to u squared. And then finally we need a replacement for that square root of u squared plus a squared. And we'll go ahead and get that in just a second. Okay, so there's your du, a secant squared theta d theta. Our u squared is a squared tangent squared theta. And then we need to go get the square root of u squared plus a squared. So the secant is going to be the hypotenuse over the adjacent side, and then we can go ahead and move that a over. So a secant of theta will equal square root of u squared plus a squared. So we can go ahead and put an a secant of theta in its place. And then we can do a little bit of simplification. And we got a 1 over a, 1 over a squared. So we can get this a and this a to absorb. Factor out the 1 over a squared. It's constant. And provided that a is not 0, of course. And let's see what we got going on there. So we got a secant squared and on the top and a tangent squared on the bottom. And so let's see what happens there. Okay. Well, it's not quite a secant squared. Pardon me. So this secant will absorb one of the secants there. So we'll rewrite that as a 1 over cosine, and then the reciprocal of tangent is going to be cotangent, which is cosine over sine, and then of course they're squared, so we'll make them squared instead. So we can do a little bit more simplification there. 1 over a squared, and then that'll be cosine of theta over sine squared of theta. And now we could do a U-substitution, so you have to be a little bit careful because in the original formula we had u, so this is a different u than the one in the formula. So u is equal to the sine of theta, du is equal to cosine theta d theta. So that'll give us 1 over a squared integral of 1 over u squared du. Again, that's a different u. Okay, so that gives us 1 over a squared, and it'll be minus 1 times 1 over u plus constant of integration. Okay, so that'll be negative 1 over a squared. 1 over u is sine of theta, so that'll become cosecant of theta plus c. Okay, and so we can go to our triangle to get what the cosecant of theta is, and that's going to be the hypotenuse over the opposite. So the hypotenuse is the square root of u squared plus a squared. Okay, you have the minus sign there, all over a squared, and then times u, which is the hypotenuse. Oh, not the hypotenuse, is the opposite side, plus c. Okay, and so there we are. That is our formula if it was a plus in the denominator there between the u squared and the a squared. Notice that these are opposite signs, and you see the minus plus and then the plus minus there. Okay, so that's half of it. Now we have to do the other case where it's a minus in the radical there. Okay, so formula 35. Okay. So u squared and then u squared minus a squared. Okay, we'll again do our triangle. This one probably we're going to want to use kind of the secant setup. Okay, so hypotenuse will be u, the adjacent side will be a, and then using the Pythagorean theorem, the opposite side will be the square root of u squared minus a squared. Okay, so the secant of theta is going to be the hypotenuse over the adjacent, so a secant of theta will be equal to u, and so that gives us a way of substitution for u. We'll go ahead and do the differential of both sides so we can get a substitution for du. So we have a secant theta tangent theta d theta is equal to du. We can also square the equation there and get u squared is equal to a squared secant squared of a theta, and tangent of theta is going to be the opposite, which is that radical, over the adjacent, which is a, and then we can go ahead and multiply by a to move it on over. Okay, so we got everything we need, so we'll replace that du with a secant theta tangent theta d theta. We can replace the u squared with a squared secant squared theta, and we can replace the square root of u squared minus a squared with a tangent of theta. Okay, so things will simplify down, so let's see what we can do. We can absorb an a, so we'll have an a squared in the denominator. We can absorb a tangent of theta, and we can absorb a secant of theta. So we have 1 over secant of theta, which is cosine of theta, d theta. And so that's a little bit easier than the previous one, so that integrates to 1 over a squared sine of theta plus c. Go to our triangle to get the sine of theta, which would be the square root of u squared minus a squared divided by u. Okay, and there is our formula 35. So this one was a little bit easier. The other one, the trig integration, the substitution after we did the what am I trying to say here? The trig substitution and the resulting integral was a little bit less demanding than the previous case there. Okay, so we're going to go and work through a couple examples of trying to find the formula. So this is your Appendix B in your textbook. So we're going to speed this up. Integrate using tables. Okay. So we're going to look at an integral of 1 over x squared plus 4x plus 8. And looking at this right now, this looks like it's probably going to be an arctan if we go ahead and complete the square. And so if we need to complete the square, we need x squared plus 4x plus 4. So we're going to borrow 4 from the 8 there. Okay, so there it's all there. And so complete that square, 1 over x plus 2 quantity squared plus 2 squared dx. Okay. So this is going to be formula 23 from the appendices, which is exactly the Arctan formula. So this isn't really that new, but we can use this to kind of get some practice in with the integration by tables. So to get it to fit the form, your u is going to be x plus 2, du is dx, and the a will be 2. So we'll go ahead and use that. So it's going to be 1 over 2 arctan of x plus 2 over 2, and then plus c. Okay, that one's pretty straightforward. Wasn't too much going on there. Some of them you have to be a little bit clever, and we'll get into an example or two a little bit more complicated. So number 2, we have e to the x over 1 minus the tangent of e to the x dx. Okay, and so you'd have to go through and you look through your tables. You know, if you got like that e to the x there, that looks like it's probably going to be like my U-Substitution. U is, you know, e to the x, du is e to the x dx. That's what I'm thinking there. So in my integration tables, I'm probably looking at something like a du over 1 minus tangent of u. That's what I'm going to look for. And so looking through my tables, I find this formula 71, which says 1 over 1 plus or minus the tangent of u du, and that's pretty much exactly what I'm looking for. And so this is what the integration by table says. It's going to be 1/2 u. 1/2 times the quantity u plus or minus natural log absolute value cosine u plus or minus sine of u, and plus c. So to get the form there, our u will be e to the x, and our du will be e to the x dx. So then this becomes 1/2, and then u, which is e to the x, plus or minus, and so which one is it going to be? We have an exact match here and here, so because this is minus, in those two locations where you have that plus or minus, it's going to be a minus. So 1/2 times quantity e to the x minus natural log absolute value of cosine of e to the x minus the sine of e to the x, and then plus c. Okay, so that one wasn't too bad. Might have taken a little bit of time to kind of figure out which one it fits in your integration by tables. Let's go ahead and look at one more. So we're going to look at x squared times the square root of 2 plus 9x dx. Okay. And so looking through my table, I'm probably going to look at, you know, the ones that have some sort of radical, also the ones that are going to have like a u squared, maybe a u squared on the outside. That's what I'm going to kind of look at. And so specifically I'm going to look at formula 27, which says the integral of u squared, square root of u squared plus or minus a squared du, which more or less looks like that. So we're going to see what we can do with that. That's going to be equal to 1 over 8 u times quantity 2u squared plus or minus a squared times u squared under the square root plus or minus a squared minus a to the 4th natural log absolute value u plus u squared plus a squared, and that u squared plus a squared is under the square root, and plus c. Okay, so isn't that just a wonderful integral? I think there's supposed to be a bracket here. Okay, so quite a mess, and so we want to try to get it to kind of fit the form there. And so I'm thinking if I'm going to get it to fit the form, let's see what we need. The a would need to be the square root of 2, so that when I square the square root of 2, I'll get the 2. The u should be 3x, because 3x quantity squared would give us the 9x squared, which means I need a 9x squared on the outside of the integral there. I only have an x squared, but we're only off by a constant, so I think we can fix that. Du will be 3 dx, so let's see what we can do with that. Alright, so I'm going to go ahead and put in a 3x squared. Okay, so I'm just going to go ahead and do that. We'll figure out about offsetting that in a minute. So I need to divide that by 9. Okay, so that'll turn that back into an x squared. And then we have the square root of 2 quantity squared plus 3x quantity squared, and then times 3x 3 dx, excuse me. And so there's the 3 there, and then I need to divide by 3. Okay, so we've offset everything there. So now we have an exact match there. And okay, and so let's go ahead and integrate this. So the 1/3 times the 1/9 there will be 1 over 27. and we multiply 1 over 27 times 1 over 8, that's going to give us 1 over 216, and then it's going to be u, which is 3x, times 2u squared, so u squared was 9x squared, so times 2 will be 18x squared, plus the square root of 2 squared, which is, the square root of 2 squared is going to be 2, and then square root of 9x squared plus 2 minus the square root of 2 to the 4th will be 4, natural log of 3x plus the square root of 9x squared plus 2, and then plus your constant of integration there. Okay, and the last example we're going to look at is a definite integral. So it's the definite integral 0 to 4, and it's going to be x over the square root of 3 plus 2x dx. And so I'm going to go look through my integration tables, and it looks like it might be formula 21. And formula 21 says u divided by a plus bu under the square root du is equal to negative 2 times 2a minus bu all over 3b squared times the square root of a plus bu, and then plus c. So if this is going to be an exact match, let's see what we got going on here. So the u should be x, your du will be dx, so that looks good. A will be 3, b will be 2, and so this looks pretty straightforward here. So we'll go ahead and do this now. So we got negative 2, and then 2 times a, which is 2 times 3 is 6, minus bu, so that'll be 2x, okay, over 3b squared, so b is 2, so that'll be 4, times 3, that'll be 12 on the bottom, square root of 3 plus 2x, and then we're going to evaluate that from 0 to 4, and so after doing some routine evaluating there, this will end up being 1/3 square root of 11 plus the square root of 3. Okay, so that's it. You know, you can look at the textbook for more examples, but that's essentially what integration by table is. We just got to figure out which formula it'll end up fitting. Okay, so we'll see you next time.